In this fundamentals video, we'll break down the advantages of using AWS's network by leveraging VPC endpoints instead of NAT gateways, and feature a live experiment to showcase the real cost and performance gains. Hi everyone, my name is Rob from RobUps, and today we'll be talking about how you can optimize your egress traffic using VPC endpoints. Before we jump into the video, I want to talk a bit about NAT gateways and VPC endpoints. Typically, when setting up a network, you need a tool to allow outbound or egress traffic. Traditionally, for most egress traffic, NAT gateways or NAT instances are viable tools. They allow egress from your subnets out to the internet to all different types of traffic. NAT gateways support all types of egress traffic. An alternative, if you're talking to AWS services specifically, is something called VPC endpoints. These endpoints bypass the need to go out to the internet and communicate directly with AWS's internal network, creating a faster and cheaper alternative for your egress traffic. In this experiment, we'll set up a simple architecture where we have an EC2 machine running in a network and communicating directly with an S3 bucket. During the experiment, the EC2 instance will send payloads to the S3 bucket and read them back, displaying the latency of each operation over each iteration. This experiment will generate data in our S3 bucket, and we'll run it twice, once using a NAT gateway and the second time using a VPC endpoint. At the end of the experiment, we'll be able to see the differences in the network traffic generated across our NAT gateway, and we'll be able to see the latency of each option with our traffic going through the NAT gateway and the VPC endpoint. With these results, we'll be able to have better performance metrics over both options, as well as be able to forecast the costs of each solution over time. So with that, we'll take a look at experiment number 1. In this experiment, we'll be running a simple architecture where our EC2 machine is communicating out our NAT gateway directly to an S3 bucket. Before we jump in, I would like to encourage you all to check out the code that's available publicly on my repository, linked in the description of this video, and follow along for yourself. Now, with that said, let's jump into the code. Now that we're in our workspace, we're simply going to open up the project folder, and we're going to see a few things. We're going to see a typical collection of Terraform files, our main TF, outputs, variables, and versions. And we're also going to have a load test.sh. For the purposes of this experiment, we're just going to run the commands directly available in the README and walk through them. The first command is simply going to be applying our Terraform. This will spin up the architecture that was shown in the previous slide with the enable S3 endpoints false, since for experiment 1, we're going to be using NAT gateways. So in order to do that, I'm just going to copy this command here into my terminal and apply. All right, and after a couple minutes, our Terraform has completed successfully, and we have all the outputs we need to proceed. In the next step, we're going to be using AWS Session Manager to log into our EC2 machine that's running and execute our load test script. To do this, we need to run the SSM start session command and connect directly to our EC2 instance. If you look at the outputs of our Terraform, we've outputted the exact string that we'll need to run next. To do that, we're going to simply copy the command directly from the output. And now we'll just execute this command. And we'll see that we've started a session on our machine. Now, before we do anything, we just want to test that our instance has been loaded with the appropriate parameters. And so to do that, we're just going to simply run the first few steps on lines 7 through 9 in our README. So first, we're going to go source ets profile.d/experiment.sh, and then we're going to just going to simply echo the test bucket and make sure that it aligned with the bucket we created in our Terraform. And as you can see, VPC Endpoints demo S3, so it looks good. It looks like we were able to successfully pull the details from our shell script. So now, before we run anything, we're going to go and copy our traffic.sh script into our instance in the running session to kick off the experiment. If you're interested exactly in what this load test is doing, you can simply check it out in the load test page. But in a short summary, it's essentially going to be spinning up workers, and these workers are going to be executing put requests on our S3 bucket with files of around 250 megabytes in size. And then it's going to also be running GET requests against the information in those payloads. And so with each iteration, we'll see a GET and a put, and each cycle will be done by one worker. And so if we're running this with 2 workers over 60 seconds, we should be running about 20 to 40 gigabytes in traffic through our NAT gateway. So in order to simulate that, I'm going to simply go back to here and copy everything from the cat line into my session and click enter. And as you can see, our experiment's kicked off for an duration of 600 seconds with 2 workers with 256 megabytes in size. We're going to let this experiment run for 10 minutes and come back and see the results. So as we can see, the experiment wrapped up at just over 100 iterations, and we can go check out the metrics that we generated on our NAT gateway. So if we go back over here to the console, we can see our NAT gateway. And so we're simply just going to copy the NAT gateway ID, and we're going to go over to CloudWatch, and we're going to go to all metrics, and we're going to search by our NAT gateway. So in this case, it's here. And what we're going to look for is the bytes out to destination. And then we can look at it in a graph or a line graph. And so as you can see, over the last hour, we generated approximately 30 gigabytes of traffic through our NAT gateway. And we're going to use this over the period of about 10 minutes to extrapolate for our overall calculation. Switching back to the code view, we can actually see the latency of each of our put and get requests over each iteration and worker. So we're just going to copy this information as well to contribute to our results. For the second experiment, we're going to use a gateway endpoint, which is essentially a VPC endpoint for S3. Instead of going out through our public subnet and out to the internet, we're simply going to traverse the AWS backbone directly to our S3 bucket. In this experiment, we should expect a lower latency and much lower cost. Let's switch over to code view. So now that we have the results from that session, we're now going to actually enable our VPC endpoint and rerun the experiment. And this time we'll be using an S3 Gateway endpoint instead of the NAT Gateway. So to do that, we're just going to switch the var to enable S3 endpoint true. And so before that, we're just going to exit our session, and then we're going to reapply this Terraform. Now that that's completed, we're actually logged back into or start another SSM session by copying the exact command. And we should be getting into a session. So now that we're in, we actually don't need to copy everything because everything should be already copied in from our last run. So we're simply going to run source etc profile.d experiment.sh, and we're pretty confident on all of the parameters, so we're just simply going to run the VPCE traffic.sh file and run it again. And now this should be running through our VPC endpoint instead of our NAT gateway. And if we just move back to the slides, we can very quickly look at the VPC endpoints that are available in our console. And we can see we have a gateway endpoint for S3 and all of the traffic. If you can see the route tables, we've added this route table to our subnet. So all of the traffic should be going through this gateway endpoint. So we'll switch back to the code view. So our experiment's wrapped up and we can check the results. As expected, our bytes out to source through our NAT gateway have gone to 0 since we've been traversing the AWS endpoint. Similarly, if we go back to the code view and collect our latencies, we'll be able to perform a comparison on the average latency across each iteration. So after crunching the numbers, where did we land? Well, as we can see, the latency decreased across our put and get endpoints by about 4 to 5% when we switched from the NAT Gateway to the VPC endpoint. We calculated this by looking at the average latency across every iteration of both experiments. In addition to that, we actually saw a 100% cost decrease, and after extrapolating the 27.5 gigabytes over 10 minutes through our NAT Gateway across a month, this would have ended up costing us around $5,378. Now, as we saw in the experiment, our traffic to our NAT Gateway actually went to 0 once we implemented the S3 Gateway endpoint. As a result, our costs go to 0, at least when it comes to our egress through our NAT Gateway. So as you can see, we did get a slight performance increase through our latency by switching from a NAT Gateway to a VPC endpoint. In addition to this, we actually saw a significant cost decrease. And so the recommendation here is if you do have any workloads that are speaking to AWS services directly through a NAT Gateway, there's an opportunity for you. AWS offers a variety of endpoints across many of their services. And so if you do have this opportunity in your stack, this is a bit of a no-brainer. You'll save on costs and you'll get a performance boost from the latency. And with that said, I just want to say thanks for watching. I hope you enjoyed the second video in the AWS Fundamentals series. And if you're interested in future content, please feel free to like and subscribe. Thank you and have a great day.